Digital electronics is at the heart of every modern electronic device, from smartphone to laptop to satellite and medical equipment. It lets us process information at an incredible speed and scale. Think about the video you're watching right now. It starts as raw pixels captured by a camera. Those pixels are converted into digital data, billions of ones and zeros, compressed, packetized, and sent across the internet. Inside servers, routers, phones, and laptops, millions of tiny digital circuits, logic gates, flip-flops, adders, decoders work together to move this data. When the data reaches your device, another chip decodes the compressed ones and zeros and reveals the video frame and drives them to the display. Every step, capturing, encoding, transmitting, decoding, and displaying is powered by digital circuits designed by VLSI engineers. And it all starts with writing the register transfer level or RTL code, describing the functionality of the chip. In physical design, we translate this RTL code, which is a behavioral description of the digital design, to the blueprint of real geometric structure to be built on silicon wafer. We do it in multiple stages. First, translating the RTL, the behavioral description, to logic gates. Then place and route those logic gates, and finally sign-off verification to ensure we preserve the functional integrity during the translations. To ensure the chips run at multi-gigahertz speed, we calculate the resistance and capacitance and delay of each of the tiny wires in our chip. We do it at picosecond level precision. To give you an idea how small a picosecond is, let's consider light, the fastest known thing in the universe. It can travel from here to the moon in just about 1.3 seconds. How much distance do you think it travels in 100 picoseconds? Around this much, 3 centimeters. We have to consider real-world effects like temperature and voltage variation. Let's think of an extreme case. Chip is going to the space on a satellite. It might see temperature variation from minus 150 degrees Celsius to plus 120 degrees Celsius. If you remember from electrical engineering courses, resistance dependent on temperature, and this wide range causes the circuit delay to behave in a wide swing. We must ensure our chips are working at the desired performance level across all these temperature ranges. Fortunately, we have very powerful softwares we call EDA tools to help us do all this. Naturally, these softwares are very complicated and need special training to use. Think of sitting in the cockpit of a jet airliner. You don't know what all those switches do without proper training. At UVTI, we will dive deep in all those concepts and learn how to use the tools to design the chips, leveraging theoretical knowledge. Instead of focusing on the tools, we will focus on the actual design challenges and concepts. We will go through real-life examples of different issues through test cases. We emulate a real-life project environment in our training to help the students navigate the complexities and teach soft skills to utilize the time more efficiently. In this professional course offered for graduate electrical engineers, you will revisit core concepts of digital electronics and VLSI. Learn how to design large and complex chips across the RTL to GDS flow. Use Linux confidently through the command line interface. And work with industry-standard EDA tools. Gain practical skills necessary to start a career as a physical design engineer.